from the Department of Psychology and Neuroscience and the Department of Sociology, and a fellow at the Carolina Population Center. And today I'll be giving you part one of a two-part introductory overview of structural equation models. Before I get started on this, I want to mention that this is part of a SAMSI program. SAMSI stands for the Statistical and Applied Mathematical Sciences Institute, and it's a National Science Foundation sponsored program. And this spring of 2021, we'll be having a program, Data Science in the Social and Behavioral Sciences. As part of that, we're recording about a half dozen didactic seminars that people who would like to participate in that program can view in advance of it. The SAMSI program is going to be open to anybody who would like to attend, and there should be more information coming out about it over the next few weeks. I also would like to thank Ilya Gudin, who helped in the preparation of these slides and getting us ready for Zoom and everything else, and he's going to continue that help today. If during the talk you have some questions, please feel free to use the chat and you can address it to everyone. Ilya will be monitoring that. If there's something that he feels would be good for us to handle at the moment, he'll just let me know and I'll stop and do it. But there'll be at least a couple of places where I'll pause and have a question and answer session. I have a couple of questions that I anticipate that some people will have. And then I'll also open it up to any questions that are not listed there. So without further delay, let me get started on this. I guess one other point is that part two of this will be next Friday, 1 week from today at the same time. And you should be able to access it using the same Zoom information that you're using to access it this time. So this is an outline of what I'll be covering in both parts. I'll briefly talk about the purpose of this overview, what the intention is. I then will have a session where I'll talk about what are structural equation models, or SEMs. As part of pulling out that meaning and trying to explain it to you, I'll have a series of a few empirical examples where I'll first consider what a conventional approach might look like, and then I'll show you how you could do it with a structural equation modeling approach. There'll be model and notation, which will be needed to explain the major steps in structural equation modeling. A little bit about software, and then we'll have an extended empirical example followed by some conclusions. Depending on the timing, and I am aiming for roughly an hour and a half today, depending on the pace that we go through this, I anticipate that we'll end somewhere around model and notation. And so that's what will be the pickup point for the next session, wherever we leave off on this outline. As far as the purposes of this overview, I really want to provide a broad overview of structural equation models and latent variables. We'll talk a little bit more about latent variables momentarily, but this is one feature that enables us to study fairly abstract variables that appear in many of our theories, or less abstract variables that we can only poorly measure. I also want to give you a feel for what the major steps are in applying SEMs, and then I want to illustrate a number of these ideas with examples. First topic, what are structural equation models? Here it's kind of interesting. Over time, I've come to realize that we really have two different viewpoints of structural equation models. And they exist, sometimes they dominate one person's perspective. One of these will dominate one person's perspective, the other will dominate another's, and sometimes it's some kind of mixture of it. And these two faces of structural equation models are first it's an extremely general statistical model. And second, it's actually a technique to incorporate, test, and assess causal assumptions that come from the researcher. So let's talk about each of these two phases of SEM in a little bit more detail. The first one, it's a general model. Well, as a general model, and what I mean by that is that we'll see there's two main equations that characterize these structural equation models. These are two matrix equations. I'll show them to you a little bit later, but they're a latent variable model, gives a relationship between the latent variables, and a measurement model, which gives the relationship between latent variables and measures. By imposing restrictions on those two equations, we can actually cover most of the commonly used methods in much of the empirical research. So multiple and multivariate regression as an example, or ANOVA analysis of covariance, simultaneous econometric type models, even principal component models or latent growth curve models, fixed and random effects models. You know, I have just a partial list here just to give you a sense of their generality. I'm also referring to them, and others refer to them, as a general model because they allow a great number of capabilities. For example, in a structural equation model, you can have both latent and observed variables. Now, I keep talking about this latent variable, and let me take a moment just to explain what I mean by a latent variable. In lots of disciplines, there are variables that are fairly abstract, that are part of our theory, but are not in our data sets without measurement error. For example, social scientists often talk about something like socioeconomic status or social class, or there's a lot of interest in happiness. You know, what type of variables determine that, or social capital. You know, the list goes on and on. Discrimination, racism, sexism. These are fairly abstract variables with real consequences. And if we look at our data sets and what are available, we don't have something that perfectly measures these fairly abstract variables. Well, these abstract variables that have theoretical importance and practical importance, as we'll see, but we can't measure exactly, these are the latent variables. The observed variables refers to, as the name would suggest, the variables that we have in our data sets. But the structural equation models allow us to incorporate these latent variables, taking into account that we can only imperfectly measure them. And we can build models that relate these latent variables to the observed variables that are in our data set, so to ground them a bit in the actual material we have in hand. We can have both random and non-random types of errors. These can be measurement errors, or these can be errors in equations. We can have multiple indicators. And what multiple indicators is referring to is because these variables are so abstract, we don't assume that any one of the variables in our data set is a nearly perfect approximation of that latent variable. So to try to better get at these abstract variables, we might have 3 or 4 or 5, even a half dozen ways of trying to measure achievement or any of these other latent variables that I mentioned. And these can just be built into the model. You don't have to look at the data set and say, well, I think this education is my best measure of socioeconomic status, so I'm going to put education in there as my proxy for SES. We can allow for linear and nonlinear restrictions on our parameters. So if we think that there should be some equal effect of two variables measured on a similar scale, we can incorporate that into the model and test to see if that holds for our particular data. Furthermore, there are additional tests of model fit that you usually don't see when you take other approaches, and this can be very revealing as well. We can allow non-normal variables. We can allow endogenous variables that are categorical, or exogenous variables for that matter, that are categorical, either dichotomous, ordinal, or censored. So that is why we refer to it as a general statistical model. It covers a lot of things, a lot of different techniques, and it can incorporate both latent and observed variables. Now, the second phase of the structural equation models that I mentioned, it is a model to incorporate, test, and assess causal assumptions. Now, the important point I want to make here is that this is not a technique that somehow reveals causality, that you plug it into a program and it comes back and tells you these are your set of causal relationships. My emphasis here is on causal assumptions. And I'm giving this emphasis now because this is one area where I think structural equation models are widely misunderstood and what their purpose is. The irony is that the people using structural equation models have never claimed that. And we can go back to Sewell Wright. Sewell Wright, if there's one person who perhaps we would say is the most important force behind these structural equation models, he called them path analysis and path models. But he developed these techniques a century ago, in early forms, very impressive. But here's a quote from him in 1934. The method of path analysis, and there we can just put in structural equation models as a substitute, is not intended to accomplish the impossible task of deducing causal relations from the values of correlation coefficients. It is the researcher who must bring causal assumptions that are defended in the models that the researchers are formulating. And what we can get out of these techniques is whether the models or models that you formulated are consistent with the data. Now, as a researcher who's building these structural models, who's building this set of relationships, we can distinguish between two types of causal assumptions. One I'm referring to as strong causal assumptions, the second as weak causal assumptions. By strong causal assumptions, these are assumptions that are built into your model where you're saying that this variable X has zero effect on variable Y. Now you're saying that X doesn't belong in that Y equation. That's a strong assumption because you're giving me the exact coefficient. If we were to estimate that model, you're telling me the exact coefficient I would find, which is zero. Alternatively, another strong causal assumption is when we're dealing with covariances. And here, just like with the presence or absence of a variable in an equation, we're saying that two errors, let's say, are uncorrelated with each other. So we have two equations. Each of those equations has an error. And you're assuming, making a causal assumption, that the covariance between the errors of those two different equations is zero. The weak causal assumptions, in contrast, this is the more common one that we're used to thinking about. This just says that this variable X influences Y. So there's a non-zero coefficient from X to Y. Now this is referred to as a weak causal assumption because there's an infinite number of values that would satisfy that assumption. Contrast that with the strong causal assumption, where we're saying there's a zero coefficient or a zero covariance. There's only one value that would satisfy that strong causal assumption. So in a typical type of, let's say, regression analysis, when we're hypothesizing that a variable belongs in that equation, that's a weak causal assumption unless you're in the unusual situation where someone is specifying the numerical value of that variable's influence on the outcome variable in the analysis. Now, I should mention on the strong causal assumptions, I'm putting zero there because that's the most common, but it also would be a strong causal assumption if you specified a particular numerical value for a coefficient or for a covariance between two variables. Now, where do these causal assumptions come from? There's several sources. Ideally, they would come from theoretical arguments, theoretical hypotheses that are formulated. You might be drawing from past research and what they have found and wanting to see if it replicates in your new sample. You may rely on things such as temporal precedents to rule out one variable influencing another because one comes before the other, or just logical arguments that you may make. And then finally, just speculation. Perhaps you're just speculating a set of relationships to see if they are consistent with the data that you're analyzing. Let me try to make that a little bit more concrete with a example here. Let's suppose we have these four variables. We have the mother's education, the father's education. So we're looking at a sample of heterosexual couples. We have mom's education, dad's education. We have the respondent's or the child's education, and we have that child's occupational prestige. Now, occupational prestige is a measure that's mostly used in sociology, sometimes in other disciplines, which is measuring a social consensus on the relative standing of different occupations. And it generally, it depends on which type of the measure you're using, but it'll often range from something like 10 to 90, just to give you a rough feel about that. So we have these four observed variables. And what I have to the right is a path diagram. And let me explain a few of the symbols here before I tell you what it's capturing. First, in structural equation models, boxes represent observed variables. These are the variables that you do have in your data set. So we're saying we've got mom's education, dad's education, respondent education, and the respondent's occupational prestige in our data set. That's why those variables are in boxes. The single-headed straight arrow, this indicates that the variable at the base of the arrow has a direct effect on the variable at the head of the arrow. So the single-headed straight arrow is representing, if you will, causal direct effects between two variables. These curved two-headed arrows, and I know it's a little hard to distinguish between them, but every pair of these epsilons, which are error terms, so these epsilons are all the other influences on the variables they point to that are not included in the model. Just like in regression, these are error terms. So these curved two-headed arrows, what they mean in structural equation models is that the variables connected by them have an association. They have a covariance with each other. There's many reasons they may have a covariance, and the model is not explaining what the reasons are, but it's just acknowledging, and it wants you to acknowledge that there is some association between those variables. So that's just some of the path notation here, which is an important part of structural equation models. Now let me explain what this diagram is. This diagram, in some ways, is a representation of this statement you sometimes hear people say, where they'll say, well, let's just let the data tell us what's going on. Well, if you're not giving it any guidance, we've got to put in all possible direct causal effects between each of these variables. So that's why we have all these feedback loops and all these single-headed straight arrows going in every direction, because we're not committing to anything. And we also, in the spirit of letting the data tell us, we're letting these errors intercorrelate with each other. All possible pairs of errors correlating with one another. Now, the problem with this, and the problem with that idea that we can let the data tell us, is that this is what's called a hopelessly under-identified model. We cannot find unique coefficients for each of these arrows. There's an infinite number of values that we could plug into these arrows that would still be consistent with the data. So this idea that we can somehow just let the data tell us without giving it any structure is a fallacy. We have to put some structure onto it. This is a good representation where, in addition to being under-identified, we have no strong causal assumptions here. And let's take a look at that a bit more closely. So if we want to identify this, it would help to bring some strong causal assumptions to this model. And if we look at these variables, some of these things are not too hard to make assumptions about. For example, how in the world would the respondent's education influence their father's and their mother's education? Makes absolutely no sense. The same thing is true for the respondent's occupational prestige. That cannot influence the parental education. So we can eliminate all the paths that are going from Z3 to Z1 and Z2 and Z4 to Z1 and Z2. We can just set those to 0. That's a strong causal assumption, but given the temporal aspects of this, it's not that difficult of one to defend. If we look at Z3 and Z4, generally, now there of course are some exceptions, but in general, a person usually obtains a certain level of education before getting full-time positions, full-time occupations. So for most in the population, it makes sense to think of the education coming first and the occupational prestige coming second. And if there's any kind of effect from occupation to respondent's education, it's more the exceptional case, and it's probably a safe assumption to assume that Z4 is not determining Z3. So there's another strong causal assumption. And perhaps the strongest causal assumption I'm making here is the assumption that these error terms are uncorrelated. Now, I've written it out in a formal expression here, but let's see what it looks like in the diagram. If we impose these restrictions on that diagram, notice that things have gotten cleaned up quite a bit. Now what we're saying is that mother's education, father's education determines the respondent's education determines the occupational prestige. So this has got some strong causal assumptions here. We could, of course, question some of these. I mean, this is strong in that it's saying that parental education effects on occupational prestige is totally mediated through Z3. Now, my diagram is saying that, but when it comes to having real data, my data may not cooperate with my model. I may get diagnostics that say, this is not a good match to the data. This would happen if, in fact, we had maybe mom's education not only having this indirect effect through Z3, but a direct effect to Z4. But this is just an illustration of imposing these strong causal assumptions on your data. Now, we do have a way of testing this model. As I said when talking about the last slide, me saying it so doesn't make it so. This model is rejectable because we have more than enough information to estimate all the coefficients, the variances and covariances that we need in this. So we can test the model where the null hypothesis is that all strong causal assumptions hold versus the alternative hypothesis that at least one causal assumption is incorrect. And there are diagnostic tests within structural equation models that enable us to do just that. So if we reject the null hypothesis, this means that one or more of those causal assumptions, those constraints that I introduced, like the covariances of the errors being 0, some of the regression coefficients being 0, one or more of those are incorrect. Or it could be that there's a major specification error. I didn't even come close in formulating this model. There's a very different structure that exists than what I formulated. Either of those are plausible if I reject the null hypothesis. If I don't reject the null hypothesis, this tells us that the data we've analyzed is consistent with the model. This is not, and this is why I've bolded this on the slide, this is not proof of the validity of the model. I think we just have to view this in a more modest way, that our model has survived this test, and we'll just have to wait to see what happens with the next test to see if it's still consistent with fresh data, same type of formulation. Perhaps if you're getting, if you want to see how it will generalize another population, perhaps, and see if it holds there. So the best we can do is not reject it. This is not proof that all our causal assumptions hold. It just means our data are consistent with the model. Now, there may be some people here who have seen DAGs, which is a more recent approach to looking at sort of causal modeling. And on the face of it, the diagrams look very similar to each other. But it is not just reinventing the wheel with DAGs. There's some similarities and there's some differences. And this contrast, I just wanted to do for the benefit of those of you who are familiar with DAGs. For example, in this classic structural equation model, which most of my talk is about, there's a convention of boxes for observed variables, as I mentioned before. There's not that type of convention of boxes for observed variables in the DAGs. More often than not, I see them as not enclosed variables. Occasionally, I see them enclosed, but not necessarily in boxes. Second, the errors of the endogenous variables are usually explicit. Now, let me explain what endogenous variables means. Endogenous are variables in the model that appear as a dependent variable in at least one equation. So in this very simple structure that we have, Z3 and Z4, these are the two endogenous variables in this model. And it's quite common to explicitly represent the error, all the other influences that might influence Z4 but aren't included in the model are in this epsilon 4. In the same fashion, all the other variables that influence Z3 but aren't included in the model are in this epsilon 3. So it's common to have the errors of the endogenous variables explicitly represented in classic structural equation models. In what I've seen in most DAGs, the errors of the endogenous variables are often implicit. There's a recognition that you need errors because we don't have deterministic systems, but they're not often written out. Here's another contrast. In the classic structural equation models, the equations usually are linear in the parameters. What I mean by that is you can have interaction terms, you can have quadratics, you can have cube terms, but you're assuming that you can add together those terms in a model that doesn't have parameters appearing in a nonlinear fashion. In DAGs, it has a more general non-parametric implicit assumption for the equations here. So here it's not assuming that they're linear in the parameters. So one nice advantage of this is that if you have proofs, and there's many nice proofs with DAGs, these hold in general, not just for models that are linear in the parameters. Now in practice, many times people using DAGs will retreat to models that are linear in the parameters when it comes to estimating them with empirical data, but it is a real advantage to have any proofs that are developed for DAGs being of a non-parametric nature. Then lastly, this curved two-headed arrow. In classic structural equation models, the curved two-headed arrow is the covariance due to perhaps omitted variables, could be direct relationship between the two variables that are linked by those arrows, or any other source. In classic SEM, it doesn't explain, it just recognizes and wants you to incorporate in your model that these two variables are associated with each other. In DAGs, the curved two-headed arrow always means a covariance that's due to an omitted variable. And this is, one contrast between the two models, and I've explicitly put it in here. So when Z1 and Z2 are connected with a curved two-headed arrow, in DAGs, it means that there's an omitted variable that's influencing both of those, or omitted variables that are influencing both of those variables. So that's another contrast. All right, let's, if you have any questions, feel free to put them up on the chat. I'm going to take a couple that I anticipate some of you might have. First one, is it okay to have more than one hypothesized model for the same set of variables? And here I would say most definitely yes. It's often the case that there are competing hypotheses and that these lead to different models. You may be working in an area and there's different schools of thought, or you may be working in an area where there's more than one discipline that's addressing the same outcome, and they have formulated their models in very different ways. So I actually would encourage people, if they do have more than one model for the same data, to formulate them. And then what they can do is they can compare the relative fit of the models to your given data. So yes, definitely, you can have more than one hypothesized model, and it's not a common practice, but I think it would be a good practice, particularly if these are formulated in advance. A second question, is there a sharp distinction between SEM as a general statistical model versus as a tool for causal inference? And here I would answer this as saying, theoretically, yes, right? We can make distinctions, and if we press somebody on it, we could find out what their purpose was. But in practice, I would say no. You're really not sure whether the person's taking advantage of the general capabilities of structural equation models, that's why they're applying it to the data, or if they are really interested in testing this set of causal assumptions that they've made and want to see if they're consistent with the data. So as I state here, it is difficult to tell sometimes in articles what the primary purpose is for the researcher. And I also think this is tied to, for a long time, there was a lot of pushback if somebody said something about causality when they're talking about an article and studying empirical relationship, particularly if it is with observational data. So I think this made a lot of researchers gun shy of even going down that road at all. I think as other approaches to causal inference have come into play, that you'll see the suggestion that they're looking at causal relations coming out a bit more in studies in a variety of fields. But there still is a fair amount of ambiguity on this. Last question that I wanted to cover, and in some sense I've already answered that near the beginning, but it bears emphasis. Is SEM intended as a causal discovery tool? And the big answer, a big no here on that. It's a way of telling whether causal assumptions are consistent with your data. We can find that one or more causal assumptions are inconsistent with our data, but we can't prove our causal assumptions are true. I mean, this is very much like Karl Popper's falsification arguments, where he says in all of science, we never can definitively prove causation. What we can do is we can reject models, but we can't definitively say that something is true. I know that sometimes people, and it is much better if you have a randomized experiment, for sure, your assumptions being made are much more plausible when you have that randomization. But even then, you'll find books on confounding in experiments, things that have affected even an experimental design. And you also have this whole question of internal validity versus external validity. So if you design something that works in a very controlled setting, is this really going to inform us out in the field? Yeah, and then as per the last slide, we can compare different models for the same data, and this might suggest different causal mechanisms, but each of these models is constructed and guided by theory and substantive considerations. This is why it can be, if you have somebody who has essentially a statistical background without the substantive background, it's very hard to use these techniques unless you collaborate with somebody who's providing the substantive expertise, because you have to construct these models that you're about to estimate. So I'm keeping half an eye here on the chat. Unless I'm missing something, I'm not seeing any questions. This would be a good point if somebody has a question or comment to suggest it. All right, I'm not seeing anything. Going once, going twice. All right, then let me continue. And again, if there's questions that come up as I'm talking, some point that you don't understand, don't agree with, you can just put it into the chat, and Ilya can alert me if I'm missing it, and I'm happy to go over it. So let's then, as part of this, trying to give you a better sense of what these models are about, let's do a contrast between 3 examples where a conventional approach might look in one way versus what it looks like or what you could do with a structural equation model. Now let's take one that's quite practical. How much is a house worth, and what determines its value? Now this is a great example, I think, of a latent variable that is not some abstract, only theoretically useful idea. You know, how many people, millions of people, are trying to sell or buy a house? And so it's very, practical question, trying to determine what's the value of that house. Now, conventional approaches, you could ask the owner, how much is your house worth? You could look at tax assessments that are often publicly available. An appraiser could do it, or a real estate agent. So here would be 4 different ways of measuring the value of the house. It would be surprising if they are exactly alike. You know, the reason is that none of these is will perfectly correspond to that abstract value of the house. You, in making that assessment as the owner or one of these other more experts, you could look at conventional wisdom on house characteristics. Does it have a garage? What's the type of the garage? How many square feet are there? Things that are thought to increase the value of the home. And at the end of the day, you're still not quite sure how much your house is worth. Well, many years ago, and I think these were both economists, Robbins and West, 1977, they had this as a focus of a Journal of the American Statistical Association article. And what they looked at was measurement error in 3 different measures they had of the value of a home. They had the appraised value, they asked the owner, and they had assessed values of the home. And they also had a collection of variables that are thought to impact the value of the home. And they wanted to see what impact they did have on that. Here we see a diagram of Robbins and West's model. And this gives us the opportunity to explain some of the symbols in path diagrams. In path diagrams, the circle or ellipse represents the latent variable. In the case of Robbins and West's model, this stands for the value of the home. The boxes continue to represent the observed variables, the variables that are actually in our data set. If we see Z4 through Z sub NZ, these are the exogenous variables, or variables that are determining the value of the home. We'll see on the next slide what some of these variables are, but they're things like lot size, attached garage or not, things that are thought to either enhance or decrease the value of a home. This straight vertical bar with the little arrows coming down from it, this is a shorthand notation to replace all possible pairs of variables, Z4 through Z sub NZ, being connected with two-headed curved arrows. And as I mentioned earlier, the two-headed curved arrows represent an association between variables. So rather than drawing in all possible pairs of curved two-headed arrows between these variables, this is a replacement that is a bit simpler and neater. As long as you understand its interpretation, there should be no problem. It's saying that Z4 through Z sub NZ are variables that are associated with each other or may be associated with each other, but the model takes them as given. It doesn't attempt to explain the reason for that covariance. So each of these have an impact on the value of the home. And then we have the three estimates of how much the house is worth. We saw on the last slide that these were the appraised value, the owner's value, as well as the assessed value of the home. Each of these are thought to be influenced by the value of the home. This influences those judgments and estimates of how much a house is worth. We have three error terms, Z1 through Z3 here. This represents the fact that we don't expect the latent variable to completely determine each of these estimates. That another way of saying this is each of the estimates has some error in them, which are captured by these epsilon terms. This epsilon here, this is a different type of error or disturbance term, and I'm using those terms interchangeably. This is all the other factors that influence the value of the home, but are not explicitly included in the equation, very much like a regression equation. This next slide will show some of the variables, so let's flip to it. L1, as I said, is the latent variable. This is the value of the home. Z4 is lot size. Z5 is square footage of the home. Z6 is number of rooms. And they have a number of other variables that are thought to influence what the value of a home would be. And finally, Z1, 2, and 3 are the appraised value, the owner estimate, and the assessed value. One bit of explanation on this NZ notation. N is used to represent the number of. And if you want to know what number of is referring to, you look to the subscript. So this NZ is the number of observed variables. And so in total, there are NZ variables in observed variables in this model and just a single latent variable. Here are empirical results taken from the Robbins and West article. Here are the three indicators of the value of the home: the appraised value, the owner estimate, and the assessed value. Here, this alpha is like a regression intercept or constant. And the lambda is like factor loadings. For those of you who've had factor analysis or familiar with it, these are like factor loadings. For those of you who have not had factor analysis, these are just regression coefficients that you would get if you regressed these three estimates on the latent variable. Now, I know if you might be thinking, well, if it's a latent variable, how am I going to do that regression? Well, you're able to get estimates of it with the procedures that are in the structural equation modeling approach. So this 0 here and this 1 here, this says, look, we have this latent variable, the value of the home. We have to assign some metric to it. We have to give it a scale if we want to talk any more about it. So what we're going to do is, since we have this neutral, if you will, appraiser doing the value of the home, this seems like a reasonable person or reasonable estimate to use to scale the latent variable, to assign a metric to it. It still is saying that there is measurement error in it, but it's saying, let's just use the scale of the appraised value for our comparisons. That's why there's the 0 and 1 there. Now, the owner estimate. This is, as it sounds, just asking the person, how much do you think your house is worth? Something that is interesting here is that if you look at this 0.973 and its standard error, it has a very similar regression coefficient, as does the appraised value. In other words, if the home value goes up $1,000, we expect the appraised value to go up $1,000 because that's the scaling. But we also expect the owner's estimate to go up by roughly the same amount. But what perhaps is one of the most, my most favorite aspects of this analysis is that, yes, $1,000 up, $1,000, the owner's estimate will go up. But look at this constant. This isn't thousands of dollars. So what this is saying is that compared to the appraised value, the owner overestimates. Owners overestimate the value of their home by about $1,300. So I thought that was kind of an interesting result from their article. And then finally on the assessed value, this shows for assessed values, there's a negative constant of about $6,000, but there's a steeper slope. These are the error variances that are here. And here these R squares, these are telling us the squared correlation between these measures and the latent variable. So we actually can see how close these three measures are to the latent variable. So the assessed value, which has the most unusual coefficients, this actually has the strongest relationship to the home value variable. It has about 83% of its variance explained by the latent home value variable. The appraised value has about 55% of its variance explained by it, and the owner estimate has about 47% explained by it. All right, so what we learned from this analysis, we see this kind of constant bias from the owner who overestimates the value relative to the appraised value. We see that the assessed value actually has the highest R squared in relationship to the latent variable, followed by the appraised value, and the owner estimate comes in with the lowest, although it is close to the appraised value. These are the coefficients that give the impact of these characteristics of the home on the home value. So this is saying if it's an attached garage, I think the omitted category here is no garage. So it's about $134 improvement if it's an attached versus no garage. Detached garage is $690. Basement garage is $1,500. So it's actually telling you how much each of these characteristics of the home is worth, controlling for a measurement error in the latent variable of value of the home. So quite different. This is quite different than just intuition in trying to determine how much a house is worth. Trying to put some numbers on. These are numerical values, and it also is telling us how good the estimates are coming from these different sources. Let's look at a very different area. Does smoking during pregnancy affect fetal growth? Now, the conventional approach might do something like choose a proxy for fetal conditions. Probably the most common proxy to measure fetal health would be birth weight. Then what's often done is the person might dichotomize birth weight into normal or underweight. If there's a substantial group that actually is much larger than normal, they might create a third category there, but normal and underweight. And then they might do a logistic regression and take this dichotomized weight variable, regress it on different characteristics of the mother. Well, here's a different approach. This is a paper which was a replication study of an earlier paper where we looked at characteristics of the mother to see what impact it had on favorable fetal growth conditions using a SEM approach to see if it replicated. And let me explain what's in this diagram. And in this diagram, the latent variable that is of primary interest is favorable fetal growth conditions, this FFGC. It's defined over here. This is what we want to know. This is a collection of genetic, environmental, epigenetic characteristics that are favorable to the development of the fetus. We have three measures of this. We have the birth weight, which is the most common one that's used. We also have the birth length in this case, and we have the gestational age. So these are all taken as indicators of favorable fetal growth condition, but we're not assuming any one of them is a perfect measure of the fetal conditions. We're leaving that as an empirical question, how close they are to this favorable fetal growth condition. Here are the characteristics of the mother. The print might be a little hard to read down here, but it's mother's weight, mother's height, whether it's a smoker or not, if it's the first pregnancy or not, was it a relatively young age for being pregnant, was it a relatively old age? All things that the literature would suggest might impact the fetal conditions. So what this model is saying is that there are these characteristics of the mother that are going to impact the fetal growth conditions, and except for the mother's height, have all of their effect mediated through this fetal growth conditions on birth weight, birth length, and gestational age. Now, this exception is made here because of possible genetic ties between the height of the mother and then the length of the newborn baby. So it has both a mediated effect, but it also has a direct effect. The girl is over here because in general, girls are a little bit lighter, a little bit shorter. There's a little bit of evidence on gestational age, sort of put in there as a safety. Notice girl is not correlated with these variables because there's not good reasons to think that they would be associated, that there'd be a covariance between the female baby and these other characteristics. And so this is quite a different approach to dichotomizing birth weight and regressing it on these variables. And in fact, we find evidence that if we hypothesize this latent variable as a mediator of these other variables, that this model has quite a good fit compared to just taking each one of these and regressing them on these covariates. So it's a more parsimonious one. It is providing support for the idea that there could be something measuring fetal growth conditions as a general latent variable that is manifest in birth weight, birth length, and gestational age. I mentioned that this is a replication study. Other colleagues and I did a study in the Philippines where we initially formulated this model and found similar support. So we did find the same support now with a US population in this study. Yeah, so we're controlling for measurement error in the way we're doing it. We are finding empirical evidence for a latent variable for fetal growth. And there's information on which is the best measure of fetal growth. It turns out that birth weight is, of those three measures, the best to measure. And we can find estimates of smoking and other mother's traits on fetal growth, by taking this approach. Here is a third example, and yet another different area. And to understand this example, I'll just give you a little bit of background. So there's many international agencies as well as domestic agencies that try to monitor how much democracy in the political system exists in countries around the world. And the main way that this is done is by relying on expert ratings, where you'll get persons who are political experts on particular countries and particular characteristics, and they'll be asked to rate, what's the freedom of the media like you know, in Argentina? What's the freedom of the media like in Ghana? You know, a wide variety of countries. So what's the freedom to organize? How fair are the elections? So it's based on expert ratings. Now, in the social science literature, there's a claim that there are biases in these ratings. Just as an example, there's an organization that has, for years, decades, provided these type of ratings called Freedom House. And they have been criticized in the academic literature as having a conservative bias when they do their ratings. You know, they tend to favor, you know, free market economies over other economic systems, and that kind of enters into their ratings of the political system. So this suggests that when you look at these ratings, there could be a confounding of the biases of the judges with the ratings that are provided. And the problem with this is that some of these ratings are actually used in, you know, policy discussions and in trying to determine how to treat one country or another. So if you get these inaccuracies in these measurements, they can have an impact on the policy taken by international agencies. Now, what's the evidence of the bias in these? For the most part, it's anecdotal evidence. A critic will look at the ratings as they come out each year, and they'll say that, well, you know, I think Sweden was not rated fairly on this, or I think that El Salvador was should have had a different rating on this characteristic. So it's kind of ad hoc examples that are just provided. And we really don't get a good sense of how systematic the biases might be in these different ratings.
And before proceeding, I think there's just a clarification on, in the previous example and in general, what it means to connect the exogenous variables like that with a single line.
This one right here?
Yeah, yeah.
Sure. Oh, I see that there. Okay.
Mm-hmm.
Sorry, I missed that in the chat. Yeah, it has the same meaning. If it's a single-headed straight arrow, it means that mother's height, in this case, the mechanism would be probably something to do with genetics. You know, the genetic makeup of the mother can have an effect on the length of the newborn child, even controlling for the more general fetal growth conditions. So there's an effect above and beyond the effect that's being mediated through the impact of mother's height on fetal growth conditions.
I think it's the clarification rather on how the mother's characteristics are interconnected.
Sorry, the leftmost?
The mother's characters.
Okay. Yes, this is, thank you for asking that, and I should have clarified it. This is a substitute for those curved two-headed arrows. So the alternative to doing this would to be drawing a pair of curved two-headed arrows between every possible combination of variables here. You can imagine how many different arrows there'd be if we kept doing that. This is a substitute saying, rather than drawing in all of those curved two-headed arrows, we're going to just do this long line with the short arrows coming from it, and that will represent an intercorrelation between all of the variables on the left-hand side. Does that answer it? Okay. Well, going in the wrong direction. Here we go. Okay. All right, so here's a SEM approach where we could attack this idea of whether there's bias in these expert ratings or not. We have multiple ratings coming from different judges. So different judges are rating, coming up with ratings for different variables for most countries in the world. We allow the ratings to depend on the variables we're trying to measure. So we're allowing these to reflect how democratic the political systems are in these countries. But we're also allowing them to possibly contain bias from the judges. And let's see what the picture looks like for this. So at the top of this picture are two dimensions, substantive dimensions of political democracy. One dealing with political liberties in the country, the other dealing with how democratic the rule is in the country in terms of the holding of elections and related matters. The X's down here, these are indicators of either political liberties, X1, 2, 3, and 4 are indicators of political liberties, X5 through XA are indicators of democratic rule. But on top of that, we're saying that there may be biases by the judges who originated these measures. So for example, Banks is a political scientist, and he came up with the ratings for X8, X7, X6, and X4. So we're allowing for some possible bias of this judge influencing 4, 6, 7, and 8, the measures that come from him. Gastile is somebody who's from this Freedom House organization that I mentioned, and he did X3 and X5. And then Sussman is another person from Freedom House. He did X1 and X2. So what this model is doing is it's not saying, well, these are totally biased measures. It's leaving that as an open question. It's saying these things probably partially reflect what they're intended to measure, but we want to see if there's evidence that they actually also contain bias, so they're reflecting the bias of these judges. So here is that path diagram again. We didn't really have any new symbols here. The ellipses, as I said, are latent variables. So the Sussman, Gastile, and Banks, these are latent variables that represent the amount of bias coming from Banks, the amount of bias from Gastile and from Sussman. Boxes are observed variables, single-headed straight arrows. These deltas are just errors, a different symbol for the errors taken from that article. And the curved two-headed arrow is saying these two dimensions of democracy are correlated. So what this is doing, and I won't go into it in a lot of detail, but just to highlight one or two things, what this chi-square is doing. This chi-square is a measure of how consistent the model we formulated and the data are. It's a little bit different where often we're looking for significant chi-squares or significant z-tests and things of that nature. Here what we're doing is we're hoping that it's not significant, because to the degree this is non-significant, there's consistency between the model we set up and the data that we're analyzing. So this last row, just to give an example, the last row says, what happens if we eliminate these three bias terms? If we just say the model's good enough without the biased latent variables from these judges. Well, this is a highly significant chi-square. So it says there's evidence against that model. In contrast, the initial model has an excellent fit because the chi-square is not significant. It's consistent. The causal assumptions here are consistent with the data. This is just a little preview of some of the diagnostics that you can have when you're using these techniques to test your model. And that's what that table is showing. In this case, because we assumed that the biases of the judges were independent of the substantive factors that are being measured, we can actually break down the variance in each of these indicators. So here are the 8 indicators. Freedom of broadcast media, freedom of print media, etc. You can see what they are. I have one column where I'm giving the percent of the measure that appears to correspond to those substantive latent variables, either the political liberties or democratic rule. So we can see X4, which is freedom of group opposition. That looks pretty good. That has about 92% variance, very close association with that latent variable. This column here is the method factor error. This corresponds to the bias. What percentage of the variance in that rating is explained by the bias of the rater? And here we can see that for some of them, this one in particular, X6, this is competitiveness of nomination process. That has about 40% of its variance due to the bias of that rater, Banks. And then finally, the random measurement error here shows you what percent is due to measurement error, I wouldn't expect these to be exactly zero, but they're fairly small amounts of purely random measurement error, even though they have substantial non-random measurement error as measured by this 38% here, and a little bit smaller, 7%. So, contrast this with picking and choosing some cases where you don't like the rating and talking about how those ratings are biased. Here we can have a much more complete breakdown of what appears to be measuring what we want to measure, what appears to be biased, what appears to be purely random measurement error. So in summary, conventional type of analyses often just ignore measurement error. In many of our disciplines, the norms just permit you to not say anything about measurement error, even though if you were asked about the variables in your analysis, you would readily admit that's probably a substantial amount of measurement error in them. Often, there's a failure to use multiple measures. A common strategy is just to choose some measure to represent some variable that's important to your analysis. Also, single equations really dominate. So we're not guided by a model. Often it's just this equation with some outcome, and we put in some variables to try to predict that outcome. And the diagnostics for model fit are often quite limited. If you take a SEM approach, you're put in a position where you have to formalize your ideas a bit more. You have a system of equations with multiple dependent variables, and there's an explicit representation of the various assumptions you're making as part of this analysis. There also is an effort made to distinguish between the measures and these abstract variables we're trying to incorporate in our model. We're not just assuming that they're one and the same. And finally, we have testable and rejectable models. There's diagnostic information here that will show us when we have inconsistency between how we formulated these relationships and the behavior of the data. Now, let me address a couple of possible questions here. If we ignore measurement error in conventional studies, aren't we being conservative? Well, this is a pretty big misunderstanding, and I still see this taught in some methodological courses where people say, well, measurement error just attenuates coefficients. So if we find an effect, it must be a real strong one. Unfortunately, that's not true. Even random measurement error, and I'm talking about fairly well-behaved, systematic measurement error, anything can happen. But even with random measurement error, you can get biased estimates of the effects you seek. If greater than one variable has measurement error, the direction of the bias is really difficult to predict. And this other point, I think, is underappreciated. Bias spreads to even those variables or covariates that are nearly perfectly measured. Now, let me tell you the danger of that. When we're doing a study, it's not unusual that there might be 2 or 3 variables that are explanatory variables in our model, and we're particularly interested in assessing what their effect is on some outcome. But at the same time, that we put a lot of effort into perhaps getting the best measures we can of them, when it comes to control variables in the analysis, we may take a more casual attitude. We may say, well, SES is probably a potential confounder, so I'm going to put education in there. Or I'm going to put income in there. Well, here's the difficulty. If you do that, and that is an imperfect, quick decision, let me control for SES type variable, the measurement error is going to be present in that variable, and that will bias the coefficients even of a perfectly good measure in your analysis. So despite the fact you're not particularly interested in this group of control variables, if they have measurement error in it, it's going to mess up, has the potential to mess up your analysis of the variables that are really of interest to you. Here's another question. If bias estimates result, then why do nearly all studies ignore measurement error? I ask this question myself quite a lot. And here's the best explanation I can come up with. One, I've already mentioned. I think there's a widespread mistaken belief that measurement error always biases estimates toward zero. I think that's part of the problem. Closely related to this, there's a general lack of knowledge of the biasing consequences of measurement error. It's just not taught that extensively in many courses. Another factor, I think there's also a lack of awareness that we don't have to do it that way. It's possible to take account of measurement error, even if we don't have multiple measures of a concept. We can actually estimate models where we make assumptions about the amount of reliability of this indicator we have, maybe at 2 or 3 different levels. And we can incorporate that into a structural equation model and just see if our central findings are robust to those different reasonable assumptions on how much measurement error there is in other variables in the analysis. And the other reason, I believe, is that we're all quite interested in the relationship between different substantive variables. Often there's less interest, much less interest in how to measure these variables. You know, somehow that's seen as less important to really resolve. But the irony is, to the degree we're doing a terrible job with our measures, we're going to undermine our goal of looking at how variables are related to each other, the substantive variables that we want to study. So it's just not a good reason to ignore it. Here's another question that I occasionally get. I'm using a well-established and widely cited scale composed of multiple measures. Doesn't that give me the same results as a structural equation model? Not necessarily. There are several issues that are common with scales. One issue, let's suppose we have a great scale. It is only measuring the intended latent variable. So we have a scale of depression, and those items are really good items on depression, just a single dimension of depression. Even if that's true, when we add the items together, yes, it will be more reliable than any one of those items, but there still is measurement error in the scale, and sometimes quite substantial. So if someone says, well, I have a reliability with the scale of 0.75, well, that still means there's 25% of the variance that's due to measurement error. That could be enough to bias your results, particularly in combination with other variables that are also in that analysis that have measurement error. Now, in giving that illustration, I had the hypothetical that we had a great measure of depression, just measuring a single dimension. You know, over the years, I've looked at lots of scales, and it is highly unusual for me to find a scale that is truly unidimensional, doesn't have different dimensions. And as a result, when people are using these scales, they're adding together different components, different things that may or may not relate to other variables in the same way. You know, if you can imagine in the physical sciences, if they combined weight and temperature and this, that, and the other, adding them all together, and were surprised when they didn't find a strong relationship to some other variables. I see that's what we're doing in a lot of areas. We're taking multidimensional characteristics that are in these scales, we're just adding together, and we're putting them to an analysis, and we're expecting that to give us good results. Now, what does it mean if there's actually 3 latent variables that are being measured by these scale items? We add all those items together, then we get a coefficient for that scale. What does that mean? Does it mean that the first latent variable has this effect on the outcome, or the second does, or the third, or some combination? You can't tell. So most of the scales that are out there were developed with a different technology, often, Chromebox Alpha or something of that nature, which was great when it was developed, 1950. It's 70 years later. We have much better techniques now, and it made unrealistic assumptions. Chromebox Alpha assumes that you have a single dimension you're measuring. It assumes that each indicator has the same relationship to that single dimension you're measuring. It assumes that each indicator has the same amount of error variance. I just don't see it in a lot of the scales that I come across. So the SEM explicitly models the dimensions and the fit of the data so you can look at those type of questions. And it also allows you to look at the relationships between latent variables controlling for measurement error, whereas scales do not. So we can actually study the relationship between depression, removing the measurement error, and anxiety, with a bunch of indicators, removing the measurement error, or fetal growth conditions and later health conditions. There's a whole series of things that we can model in that fashion. Now, I did see, looks like in the chat, a question came up. Let me take a look. All right, so what does the SEM diagram look like when the latent variable is one of the independent variables rather than the outcome? You just would draw, for each of the independent variables, you would draw a latent variable, and then you would have its indicators coming off of it. So it would look just like the dependent variable ones we've shown, except it would just be an independent or a explanatory variable in the model. Does that answer your question?
There's also an example coming up in the next section of that.
Yes. Well, let me.
Just as a heads up for the.
No, that's a good idea. It's just that I'm conscious of the clock, so it's 3:20. But that's a good suggestion, Ilya. Let me flip up rather than trying to draw figures in the air. Here. This is what it looks like, Stephanie. So these are explanatory variables: behavior at time one, attitude and subjective norms. And here are the multiple indicators of those explanatory variables. So our explanatory variables have multiple indicators, and our endogenous variables or dependent variables have multiple indicators in that example. Okay, so that did it. Now, given the time, I think it would be, I'm happy to take questions, but this is probably a reasonable stopping point rather than just getting part of the way into the model and notation. So I'm happy to entertain any questions on what we've covered so far. I'm not seeing anything. There we go. Okay. Okay, so my understanding of endogenous variable is that it's a variable that affects X but not Y. Is that the same for, did you mean, well, let me explain exogenous and endogenous by, let me go back to that diagram that we just were looking at, since that has more interest here to try to explain it. In this diagram, the only exogenous variables are behavior at time one, attitude, and subjective norms. They are exogenous, E-X-O-G-E-N-O-U-S. They are exogenous because there's no equation in which they appear where they're the dependent variable. So there's no other variables influence them, just those three variables. The indicators of the exogenous variables are endogenous variables. So Z7, 8, and 9, they're endogenous. They're endogenous because they depend on this latent variable. These three are endogenous. They depend on this latent variable. We also can have latent variables that are endogenous. So we have Behavior intention is endogenous because it depends on these three variables. Behavior at time 2 is endogenous because it depends on behavior intention. Does that explain the difference? Okay. Any other questions? Okay, so can SEM handle longitudinal data? Most definitely. It's pretty incredible because you can actually, you can put, all right, so some of you must have heard of fixed and random effects that grow out of the econometrics tradition, but are used a lot in sociology, in political science, a little bit less so in psychology. Those models can be incorporated into a SEM framework, and it's so much easier to handle than a lot of the other existing ways of approaching it. Growth curve models can be handled in the SEM framework. Panel data models of various forms can be handled in this framework. And perhaps most intriguing is that you can do comparisons between these different ways of analyzing longitudinal data. So Ilya and I, in fact, are involved in a project now. We're modeling self-reported health, and we've considered, boy, probably 10 different longitudinal models for those data, and we're determining which has the best empirical fit to match this self-reported health over time. So yeah, there's tons of opportunities to handle longitudinal data.
And I'll just make a comment. I realize if people maybe have difficulty quickly typing in the answers, I guess they probably could just
Yeah,
ask.
you can unmute. If it's easier
Yeah.
to unmute, go ahead. Good suggestion, Ilya.
Can we get the slides at some point for these lectures?
Can you say that again? Can you do what?
Can we get the slides for these
Oh,
lectures?
yes. The Carolina Population Center will probably be posting these, and I'll be posting them also in a couple of weeks as part of the SAMSI program.
Sounds good, thank you.
Anybody else? Feel free to just unmute.
How do we determine when we should have like just measurement term error versus like a model term error? I think we had that in like one of the first pathway diagrams.
Okay, so the question is, when are we going to use equation errors, if I understand it right? When are we going to use equation error versus measurement error? Usually, when we have models like this one that is on this slide, we'll have both types of errors. Here's the equation error, this epsilon sub L1, epsilon sub L2. But there's also measurement error, the epsilon Z1, epsilon Z2, epsilon Z3, etc. Now, the main time where you will not have the equation errors, like this epsilon L1, epsilon L2, these are in factor analysis models, like that political democracy example I gave you. There are no equation errors. We just were having two correlated dimensions of democracy, but we did have lots of measurement error. We had indicators that were measured with error. Does that answer your question?
Yes, and for model errors, are they just kind of like, are the arrows usually diagonal like we have it up here?
Just like here, these are measurement errors here in this diagram. You see these?
And the model ones are usually diagonal up there. Is that the notation, the model errors?
Right here?
Yeah.
Oh, no, they can be any,
Okay.
the way they fall can be any way. You can use it as a part of your artistic expression. So whatever you think looks good to you. Anybody else?
or Ken, just an idea from the previous question is that because of that, you would also have R square terms for both the indicators and latent variables in these models.
That's right. So as Celia is saying, we'd get an R squared for this latent variable. How much variance in the latent variable is explained by these three latent variables? How much variance in this second latent variable is explained by this one latent variable? How much variance in this measure is explained by this latent variable? So there are lots of R squares that you get here for each dependent variable in the model. All right, if we don't have any other questions, thank you for coming. And for those of you who are able to do it next week, look forward to seeing you then. Thanks again. And thanks to Ilya for your help.